Okay, today is the 18th of July, so we're going to have exam number 6 in a few minutes. We also have homework set number 14 to talk about. So we'll do those things and hopefully it'll all come out nice. So does anybody have any question you'd like to go over regarding the test, exam number 6 right now? Alrighty then, we'll go right ahead and move into the next thing. Let somebody ask a question.
I have a question. I just trying to find it. When you ask for the full conclusion for the number 2 on the practice test,
Yes.
and you say, I guess the answer says it's 95% confidence. Is it always 95% confidence?
No, it's whatever 1 minus alpha would be.
You didn't give us alpha.
So then it's 5% if I don't give it.
So if you don't give us alpha, it's always
5.
1 minus.
Okay. If I don't give you alpha, alpha is always 5%.
Okay.
If I give you alpha, or if I don't, when you do the full conclusion, the confidence amount is 1 minus alpha. Okay. All right, any other question about anything? All right then. So, yeah, I'm gonna try getting this textbook information out so that we can look at it. All right, so we're in chapter 10, and we need to kind of put this into a little bit of context here so that you can understand how we get to this from where we were. When we talk about the purpose of statistics, what are we talking about? What's the answer to that question? What's the purpose of statistics?
Data-driven decisions.
And what does that mean?
What to expect.
And what does that mean?
Any data value is 75% is unlikely, and anything above 95% is likely.
Okay, so if we have something that happens 5% or less, then we say that's no, quotation marks. 95% or more, we say yes. What is the process of statistics?
Using the sample to understand population.
Okay, we're using the sample to understand the population. What are the two main, pardon me, what are the two main methods that we use in order to make that happen? Confidence intervals and hypothesis testing. Those are our methods. What's the purpose of the confidence interval? Crystal Wright, can you tell me the purpose of the confidence interval? Okay. Mara, can you tell me the purpose of the confidence interval? Mariah, can you tell me the purpose of the confidence interval? Tia, can you tell me the purpose of the confidence interval? Lana Schmidt, can you tell me the purpose of the confidence interval? Mariah, can you tell me the purpose? I'm sorry. Alyssa, can you tell me the purpose of the?
It's to, yes, locate the true value of the measurement of the population with subject viewpoint.
Yes. I thought about putting that on this test as well and putting it on every test from now on. Because I actually want you to know the answer to that question. What is the purpose of the confidence interval? It is to measure the population. The rest of that stuff is good, but the main idea is the confidence interval is supposed to measure the population based on the sample with a certain amount of confidence. What's the purpose of hypothesis testing?
Prove it.
Prove a difference. Now we have done this, and I'm going to kind of assume that most people would know the answer to these questions, even though they don't tell me what they are. But the fact of the matter is you should know these things, because this is really what we're doing. If you don't know what you're doing, you're not going to be able to answer the questions. For example, on the test, when I say, what's the answer to this? And I'm referring to this right here, that you're supposed to be able to get down to the end of hypothesis testing, and you're supposed to be able to prove a difference. And you would need to be able to explain that in the sense of, I want to understand the population based on the sample. And that needs to be in your answer. That when you answer something, you're talking about a population, and that measurement is different from something. And you need to put that into your answers. And that's important to know on the test, which we're going to have in a few minutes. So I'm going to assume that most of you know this, even though you might not have actually said it. I'm hoping that you did. Now, when we get to this point and we say confidence intervals measure the population, hypothesis testing proves that a population number is different from some other number that we're given. We had a situation when we're talking about types of comparison, if you want to say it, that the first type, we had just a single sample. And a single sample we would be comparing to a single number compared to a number. In the second type, we talked about having two samples. And we did the situation where you have two proportions. We're comparing two groups with their proportions. Now, again, the fact that we have samples is not really the big deal. The big deal is we have two different populations that we're comparing. Like all the people in Minnesota. But we don't talk to all the people in Minnesota. So we have just a sample, but what we're really concerned about is all the people in Minnesota. But now the third type that we're going to have is not like these other things that we've been doing. We're going to ask two questions. So that instead of just saying to someone, did you watch the NBA Finals? Or what's your sodium level? We're actually going to be asking each person or each measurement that we do, we're going to be doing it in two different ways. And we're going to start by talking about two numbers. So when I ask someone a question, I will say something like, what's your sodium level and how old are you? So I'm going to ask them two questions and they're going to give me two numbers when they answer those questions. And then this is what we call ordered pairs. That means we have two numbers and they are in a specific order. And when we do this, when we do ordered pairs, most of the time we're talking about X and Y. So we're measuring two things, and we call the first one X and we call the second one Y. Now, when we go through this process and we're making these things that talk about X and Y, then a lot of times we are trying to have one thing that we know and the other thing which we don't. And so this is also called the explanatory variable and the response variable. So for example, if we were doing age and sodium level, you would not say, let's see, if I change somebody's sodium level, will it change their age? No, it's not gonna. So then we say, well, if I know someone's age, what will that tell me about their sodium level? So age would be X and sodium level would be Y. That's normally how it's done. And so when we're going through this process, sometimes it's important for us to know which one we're actually talking about, right? What we're starting with and how we're, in a sense, finding out the response of that next one. Another way that this is called is independent and dependent. I don't like those terms, okay, because we change the definition of them later. So prefer not to do that. But for right now, it is something that happens out there. They say, okay, this is the independent variable. This is the dependent variable. Okay, but the major idea is just, do you understand what we're talking about here? That we're thinking about one thing which we can measure, and then the other thing is kind of a response to that. So you could say something like, well, what if we change the amount of water somebody drinks? Will that change their heart rate? So then we're going to have the thing that we changed and then the response. How does it change the thing when we do it? Now, is it possible that you could say, well, I'm going to measure your heart rate and that's going to tell me how much water you drank? Well, we could. We could do it the other way. And the fact of the matter is we don't always know how these things work. One which is, I don't know, kind of controversial, but it's out there. I just read an article about it a couple days ago. And that is, does going to college actually make you earn more money? And the fact of the matter is it might be the other way around. It might be that people who normally make more money tend to be the ones who go to college. So it's not that college makes you a good employee. It's that because you're the kind of person who's a good employee, that makes you go to college. So it's not college that changes you. It's you who are a certain kind of person, and you're the kind of person who would go to college. It's a theory anyway. But the same thing is true about a lot of other stuff. Is it true that if you have more guns, you'll have more crime? I don't know. But is it true that if you have more crime, you'll have more guns? Maybe. I don't know the answer to those questions. But to say, if I have one thing and then I also have another thing, that doesn't mean it caused them to be that way. And so even though we do this and we say, I'm measuring one thing to explain the other one, we really shouldn't necessarily say that, okay? And we'll get more into that when we define some of these terms here. But what we're talking about here, when we do this kind of stuff, is that we're going to actually make a graph with X over here and Y over here. Now, I'm pretty sure we did some of this earlier, right? And what we create is something called a scatter diagram. And let's just do an example here. Let's say we've got baseball. So here we have different salaries that are paid by different teams, and then we have the number of wins. And here we have, in 1997, you see how the points are all scattered around. This is pretty common. When you do a scatter diagram, it's going to be actually scattered. What you're going to see here most of the time is a cloud. You're not going to see things that are all set up on a straight line. That's the most common thing to happen. And if we do, this was baseball, let's say we do sodium. All right. Salt intake and ambulatory something or other. Nighttime systolic ARV. Wow, sounds technical. Great. So then we have a bunch of dots. Now, what is this line through here? Does that tell us what is happening? And the answer is no. You need to be very well and clear about this right here. This line is not telling you what's happening. The dots are telling you what's happening, not the line. The line is going to tell us something, which we'll get to in a minute. But if you ask the question, what is my purpose in statistics? My purpose in statistics is to know what's happening. The line is not what's happening. Most people, when they say, can I draw a line with these points? They think the line is the explanation. They are wrong. The dots are the explanation. The dots are what is happening. So many times when I see any kind of research article or explanation or people saying things about stuff, they say, oh, well, this is what's happening, but it's not. The line is not the thing. The dots are the thing. Okay, we got that hopefully cleared up a little bit. So then, when we say, here's a scatter plot, and it makes something happen, we can then have what you can call a description of that relationship. What does it actually look like? And here are the different kinds of relationship. We've talked about this already. So this is a positive linear relationship. Why is it linear? Well, it's kind of on a straight line. It's positive because this increases for y when increases for x. So increase in x, increase in y, that's positive. This is negative. An increase in x is a decrease in y. Most of the time, that's how we're going to answer the question at the end of the problem. We're going to say, as this thing increases, this thing decreases, or whatever. So what did they have on this thing? They said sodium level increases, systolic ARV increases, whatever that is. And then there's a pretty good amount of positive relationships, but there could be negative ones as well. And then what else? Well, maybe it's not a straight line, maybe it's a curved line. One example of this would be income as age increases. Most people have a time in their life when they are making the most money. And then as they get older, their income decreases. Another example is profit. If you have your things that are too expensive, nobody buys them, so you don't make any money. If you're giving them away free, people buy them, but you still don't make any money. There's some place in the middle where your profit is highest. But then we also have this cloud, and that says no relationship. It's possible that they are just dots, and there's actually not a relationship between the variables. In other words, as I change x, y just bounces around. It doesn't really change. And this is something where, you know how when you're looking at clouds and you say, you know, that one looks like a bunny and that one looks like a lightning bolt. You have to be able to kind of look at these and say, that looks kind of positive. The numbers can tell you something, but it's really important that you're actually looking at the dots, because the dots are the real story. So the line, the numbers that you get should not be the most important thing. You should look at the dots and see if they actually make sense when you put that on there. All right, so then, once we have these ideas about what's actually happening here, then we're going to have a number that we measure that is called the correlation. And when we're measuring correlation, two L's or just one? Just one, thank you. Correlation is going to ask the question, is there a relationship? Specifically here, we're looking for a linear relationship. Is it true that when we measure our measurements, that we see this pattern of increasing or decreasing, that's some relationship to a straight line? And so what we're going to do is we're going to measure something, and this correlation coefficient, okay, if it's a sample, we call it R, small letter R. And then if it's a population, I do apologize. I have to apologize for statistics right here. The symbol for the population correlation is a Greek letter, rho, but it looks like a P, but it's not.
It's kind of annoying.
Mm-hmm.
That's what it's kind of annoying.
Because we've already had P half a dozen times and it changed its definition. Now we have something that looks like a P, but it's not. So this thing here, if we knew the population, we would find this number, which is rho. But we don't know that, so we go with the sample number, which is R. Now, what does that tell us? Well, that tells us something that's related to those graphs that we had, but it actually has a more specific number attached to it. So this is on page 544 in your textbook. And can I make it bigger? I think I can make it bigger. This is the relationship between the correlation coefficient and the scatter plot. If I have things which are exactly lined up on a straight line, R is equal to +1, if that line is going up. If I have them exactly on a straight line going down, R comes out to be negative. So then what happens if they're not exactly on there? Well, if they're not exactly on the straight line, then this one has R of positive 0.9. This is R of negative 0.9. So positive is going up, but it's not completely because it's scattered about a little bit. So then this one has an R of 0.5. So it's kind of cloudier, scattered more. So what that leads us to is a scale that we use in order to understand correlation coefficient. It has 0 in the middle. It has +1 on one side and -1 on the other side. This would be no relationship. This would be strong positive linear. And this is strong negative linear. And this is also in your textbook. Right there. Strong negative, strong positive. One thing to be aware of here is that this thing is sensitive to outliers. That's one reason why I tell you the dots tell the real story. If you have a couple of dots that are way separate from your data set, then this could change a lot just based on those weird things that are not part of most of what's going on. So you have to be careful to actually look at your data and not just trust the numbers when you're doing correlation. All right, so far, we got that going on. Now, once we have this, we have found a question about a measurement, okay, where we have a formula that we can put the numbers into and we can make this happen. But the hypothesis testing is then a little bit different. What I have here, I'll put it right here, I guess. How do I do hypothesis testing? My null hypothesis will be that rho is equal to 0. And my alternative will be that rho is not equal to 0. So this is a bit different than what we had previously. So we're measuring some kind of a thing, and we're trying to compare it to this number, 0. And we say if it's different from 0, then that's what we're trying to prove, right? So it's important to then understand, what does that mean? If rho is equal to 0, that would mean no relationship. But rho, if not equal to 0, that would mean it's far enough away from there. So then we would say there is a, and then we can put in either positive or negative, depending on what it is, linear relationship. So then what would that actually look like? Well, if I go back to my baseball statistics thing, then I would say back here, if I proved the alternative, I would say there is a positive linear relationship between salaries and number of wins. Or I could say the higher the salary, the more you win. Okay? Now, this kind of a thing though, if we say, well, what's my process? What are my steps for hypothesis testing? Well, the first one is your hypotheses. This is always going to be the hypotheses, right? What's the next step on doing hypothesis testing? I need to find the critical value. Well, what's the critical value? The critical value is not anything that you've seen yet to this point. The critical value comes from a specific place in the textbook, which is, and I got to find it here. Don't think I have it in the resources. So let's go to the book. End matter. Tables. Plenty of good tables. Here we go. Table I. Table I are critical values. And for whatever reason, the instructions here, they don't use row, they use R. They shouldn't, they should be using row. Anyway, what happens here is that they're giving degrees of freedom, and then these numbers are for a two-tailed test, not a one-tailed test. So let's just say I had degrees of freedom was 10. If I had degrees of freedom was equal to 10, then from table I have 0.576. What that's going to mean to me then is that I'm going to go over here to positive 0.576 and fill in that region. And then I'm going to go here to negative 0.576 and fill in that region. So I have a two-tailed test. I warned you, this would happen. Here it is. So I have my hypotheses, great. I need my critical values. Where are my critical values? The critical values are in table I, which is in the textbook, and it has these numbers for alpha 0.05, that's generally what we use all the time. But then when I get that number off of table I have it to the right, and I also have it to the left, because it could be a strong positive relationship or a strong negative relationship. Either way is fine. So then I have a two-tailed test like this. Okay, so what's next? I need the test value. And here's where it gets a little dicey. Okay, how are we going to find the test value? The best way to find the test value is to use Microsoft Excel to put the numbers that you have into that computer software and be able to find the numbers. Now, the reason why it's kind of dicey is because we don't have any computers sitting here right now except mine. Technically, it's not mine, it belongs to school. But the one that I have is the one that we're using. So I have in the resources section, let's get there. Resources, introductory statistics. Under the notes, okay? So I'm looking at the notes section. And when I scroll down through the notes, I see something that says how to use Excel for correlation and regression. And I have the steps. So you can go through these, input the data, and make the thing happen. Okay? So I'm going to do that in about a minute. But if you have any problem with this or any question about it, you can feel free to let me know. Julie, of course, loves to talk to you guys, so that's always fine. Kathleen Fredericks, who's listed up there on the board, she's also a math person who can help you with that. But what's happening here is that if you go through the textbook, there's a really complicated process of using a complicated formula. And you could do that. But this is a lot easier, and it takes about 2 minutes. And so this is what I would expect you to do for your homework. Now, everybody in their heart of hearts is saying, but you're not going to ask us to do this on the test, are you? You are correct, I'm not. So this is not something you're going to have to do on the test. On the test, I will give you all the numbers. But I do want you to have experience based on just having a data set. How can we make this thing happen? All right, so I'm going to go ahead with this thing. I'm going to grab these numbers, and I'm going to go out to Excel, and I'm going to go to a blank workbook, and I don't care about that. Remove the files, thank you. Where does it say that? Data. Text to columns. No. Well, anyway, I guess I'll have to put it in by hand. Oh, no, I want to do this instead. If I go to Notebook and paste, and then grab it, that's better. Delimited space finish. Okay. So what I have here, and you're not going to have like 50 data values. You'll have like 6 or 7, so it won't be too much. But for any problem, you would put in your numbers and make it look like this. Now, what I'm going to do is I'm going to make this larger so that you can see it better. And like that, and like that. Okay. So here I have the number of hours that somebody's been working and how much attention they're able to pay on a certain scale. Okay. So what I'm going to do is I'm going to take this information and I'm going to use it in this relationship, CORREL. Okay, and this is on those instructions. This is the formula for how you find the correlation coefficient. You type an equal sign, you type the word CORREL, parenthesis, then you're going to have one set of numbers and then a comma and your second set of numbers. Bless you. So hopefully you see what I did there. I select one set of data, I type a comma, then I select the other set, the X variable versus the Y variable. And now when I hit enter, it gives me a number, which turns out to be this right here. One thing about Excel is that the number that you get depends on the size of the font. If your font size is too big, it'll round it off. And so I had to make my column bigger so it didn't round off the number too much. Normally it's fine, but just so that you know, that happens. So again, this is listed for you on that sheet of instructions. This is the correlation for these numbers. Now it's pretty obvious. It's almost out all the way out here. So we would reject the null hypothesis. We would prove the alternative. So we would say in this situation, there is a negative relationship. The more hours you spend, the lower your amount of attention. So this is the process of finding correlation.
Can you say that again?
Sure. What I did here, okay, I found the critical value, and this is not exactly the same as I said. I find the test value. This is my test value. This is the correlation. So then that test value, this is R. R is equal to negative 0.994. So then that's way over here. That's in my rejection region. So I'm going to reject the null hypothesis. If I reject the null hypothesis, that means I prove the alternative. So then I say there is a linear relationship here. In fact, there's a negative linear relationship. And what does that mean? Negative linear relationship means the more hours you have, the lower your attention span. All right, Hillary, does that work? Okay. All right, so now we've proven something. We've proven that there is a relationship here by using hypothesis testing. Well, so we're decent, okay, but what else do we need? Not just the correlation. The correlation says, is there a relationship? But now I'm going to ask another question, and the title for this is called regression. Regression is answering the question, what is the formula? So then what I'm going to do is I'm going to not just have a straight line, I'm going to have a formula for a straight line. I know that it's negatively related, but the question is, what is the formula for the straight line that I need for this? Well, what this requires you to do then is to understand how to write formulas for straight lines. Now, for some of you, this is like way out there, haven't seen this for a long time. For others of you, you just did this in a recent math class. It's important for you to bring those things back into your mind, okay? What does this look like? In algebra, this is y equals mx plus b. And I want to know what those two symbols mean. What does M stand for and what does B stand for? M is the slope. Yes, it is. Tell me more about the slope, Jessica.
It's how high or low or how far over it goes.
Okay. Right. I'll try to help you out a little bit there. Okay. So what slope is telling me is the rate of change. So if x increases by 1, for example, does y go up really high, or does it just go up a little bit? Or does it go down? That's what the slope will tell me. If the slope is negative, then it'll be a negative relationship. It will go down. Now, what is this B? What is that thing for? That's correct. What does that mean? What's the meaning of the y-intercept?
Where it crosses the y-axis.
Okay. What's the x value for that?
Would be 0.
0, okay? This is when x equals 0. It gives you the y value. Now, this is not always meaningful. Even though it's part of the equation, it's not necessarily part of our data set. Okay? For example, right here, I don't have anything with 0 hours. So this x equals 0 isn't part of my data, so I should not try to make that make sense because it's not in my data set. Now, like I said, this might be stuff where you're like, oh yeah, graphing lines, sure, do it all the time. Maybe not. Okay. But there's another wrinkle here. And that is if we go back to our correlation and regression stuff, there's correlation. Here's regression. It shows you how you can try to make a line actually fit in here, but then the best line is going to go right through the middle. And here are the equations, which we don't like, so we're not going to use them. All right? See all that stuff? Okay, but this is the big thing I want you to see. In algebra, it looks like this. Y equals mx plus b. But in statistics, for this textbook, different textbooks have different ways of doing it. For this textbook, y prime is equal to a plus bx. Well, which number is the slope? B. So previously up here, b was the y-intercept. You do y mx plus b, but now b is the slope. And this number is the y. Now I can't control statistical traditions, okay? And the textbook author did what they did. All I can tell you is it's different, whether you're doing it in algebra or doing it in statistics. Then we ask the question, how do I actually find these numbers? And the answer is, we're going to use Microsoft Excel once again. So we go back here to Microsoft Excel. And what I'm going to do is I'm going to take this, and this is on the instructions again, but I'm going to take this set of information and I'm going to hit Insert. And then I'm going to click on the little thing that has dots. Pull this down so you can see it better. Right there. There's a chart that has dots on it. And I'm going to click on that little chart that has dots. And when I hover over it, it says scatter X, Y, so I'm good. That's what I want. And I just pick the first one. Here's my graph of attention. Notice it started with 8, 7, and then it goes down from there. Okay. So what I want to do is I want to figure out what is the line that goes through those points. So on the instructions, it tells you to do this. I right-click on one of these points, and I go down to where it says Add Trend Line. I click on that, and it makes a line, which is nice. I now see the line, and it goes through the points. And then I go over here where it says Format Trend Line, and I want to display the equation. I would like to know what this equation is. I click on it, it gives me the equation. Now you can't see it too well, so I'm going to change the font so you can see it better. So this is my equation for that straight line. If you'll notice in Microsoft Excel, they use the algebra form. They don't use statistics form. So I did this, and I found this equation. This is the slope in front of the x, and this would be the intercept if I took that all the way to 0. So y is equal to, and I'll round this off, negative 1.83x plus 21.2. So hopefully you can see as x increases, y will decrease. It's a negative slope, which goes along with the fact I had a negative correlation. And as you can tell, these dots are pretty close to that line. So I've got, an R that's almost -1 exactly.
So on the homework in the book, since the book gives the equation for statistics, is it going to want us to give the answer on that?
It's going to ask you what is A and what is B.
Okay.
A would be 21.2. B would be negative 183. Okay. All right, so far, maybe. So, I go back here to the notes. Okay. So now, what is the big deal for this? The big deal for this is that, I'll take this out. I'm not doing this right away. If I say y is equal to negative 1.83x plus 21.2, and this is, I'm going to use a y prime on here, like the book does. What is this thing actually telling me? This thing is telling me the estimated average of y for a specific x based on a sample. I want you to write this down. I want you to know this. It will become very important to us later. Okay? What is the meaning of that straight line? It is not telling me what's actually happening. It is not telling me where my data is located. It is an estimate of the average of my y values for each x value. And it's only based on this sample, which I did. It is not a population measurement. is a sample measure. These things I have up here are not accurate because they are sample measurements. So if I go back to my chart, I go back, like I said, I go back to my chart. Here we go. And we'll go back to this one here. Here's the relationship between salt and systolic ARB. This line right here is an estimated average based on specific X values. So if I say, if your thing here was 2,000, then I would expect the average to be right there. But this is just a sample number. This can move. This can go up and down. It can shift slowly. This red line is not telling me what's really happening. It's an estimated average for this, based on this sample, of the relationship between X and Y. All right, so what's going to happen on your homework? First of all, you're going to have to do correlation. You're going to use Microsoft Excel to find that correlation number and do hypothesis testing. You have a couple of those problems. Then you'll have regression. You'll use Microsoft Excel to find the equation of the line. You'll plug that in. And you'll have questions that say, what is this relationship? And you say, well, when this thing increases, this thing decreases, or whatever it's supposed to be. Again, if you click on the help for the textbook, it'll go through all of the formulas, which are very complicated. I recommend that you don't use those formulas, but you follow the instructions that I have on Blackboard about Excel, and a couple of clicks, you get all the stuff you need, plug it in the right place, and we're golden. All right. Hopefully that's enough information for you to be able to do well in your homework. And so we'll give you a 10-minute break. Come back at 1:50, and we'll have the next exam. I'm not sure, I'll check.
And